Up to now, we assumed that the physical address space of the process was contiguous. That means, going back to the previous slides, we assumed that each process would start somewhere in the physical memory from some point, and you would have consecutive bytes until the end of that process. A new process would be starting from the next byte, and again, it would be a contiguous space. Now, here we had the problem that, for example, assuming that process 5 was terminated, you would have a hole here instead of process 5. You have another process here between 10 and 2. If a new process was created that was large enough not to fit in any of the two, but small enough to be smaller than the sum of the two holes, we would have out of memory problem because we don't have a contiguous sequence there. And remember, we said compaction is difficult. That's something we typically try to avoid to do. There is, however, a better solution, and that is paging. So in the case of paging, you're taking the memory, the physical main memory, and splitting it into fixed size blocks. Partitions, fixed size. These blocks will be called frames. So this is for the physical address space. The whole address space, the whole physical memory is in frames. The address space, the logical address space of a process, then will be again divided into blocks of the same size to differentiate between the blocks in the physical memory and the blocks in the logical memory address space. We will call the ones in the logical address space as pages and those in the physical address space as frames. Now, all the available frames will be called free frames. So the operating system has to keep track of which frames are available, those free frames. It also has to keep track of which frames belong to which process. To keep track of that, we will construct something called a page table for each process. So once again, the page table is kept per process. Every process has its own page table. Where is the page table stored? It's somewhere in the memory. So that means it is some overhead. The page table also consumes some memory space. But as you will see, it will be quite helpful for us. So it is worth that effort, worth that overhead that it causes. How do I keep track of the page table? How do I know where in the memory the page table is? Remember the PCB, the process control block? There, when we discussed PCB, one of the things that was discussed there was the PCB contains a pointer to the page table. So in other words, in the PCB, we store the information where the page table is. So again, the page table is per process, and the page table says this page in the logical address space is stored in this physical frame. This page is here, this is there, this is there. So it's just like what we see in here. From the logical memory, the logical address space is still contiguous because this is something virtual. So we split the logical address space into fixed size pages. So we will call them page 0, 1, 2, all the way up some value. In this example, we have 4 pages in the virtual address space. In the real physical memory, we have many frames. In this example, we have only 8 frames. Note that the frame size and the page size are equal. That means a page fits directly exactly into a frame. So in addition, we keep something called a page table for this process. Now for each process, this should be repeating. But for this process, the page table says page 0 is stored in frame 1. So in the page table, the index is the page number, and the content here is the frame number. So we know that page 0 is in frame 1, page 1 is in frame 4, page 2 is in frame 3, and page 3 is in frame 7. Note that the allocated space for the specific process, now this is only one process. There are also other processes, we are not showing them here. So the allocated space for this process shown in gray pages here are, first of all, non-contiguous, because we have other frames in the memory, either free or allocated for other processes. They're not even in order. It's not going as 0, 1, 2, 3, but it's going in the order 0, 2, 1, 3. Actually, I don't care. When I try to find some space in the memory, I don't care which frame it is, because virtually, for me, in the logical address space, they are contiguous. The last byte of page 0 is in frame 1, that's the last byte here, and the first byte of page 1 is the first byte in frame 4. But anyways, after the last byte of page 0, when I try to read the first byte of page 1, I will go to frame 4 and read that byte from here. So to the process, it will appear like it's contiguous. In fact, it's not. Now, this says, first of all, let me get rid of the external fragmentation problem. We don't have any external fragmentation here. Remember what the external fragmentation was. When you try to create a new process, like process 9, this was the whole, so I was using part of the whole, the rest was just leftover. Luckily, it was large enough to fit a new process in. Process 10 was placed here. But if process 11 cannot fit here, then it cannot. So we had remember the external fragmentation problem where some leftover spaces, not only this hole here, but this hole there, another hole there, another hole there. So the sum of all holes would be large enough to host some processes, but we would not be able to put the processes there because it was not contiguous. Now, since we don't have the requirement of being contiguous, that's fine. We can still work with it. So it avoids external fragmentation. Also, it avoids the problem of varying size memory chunks because everything is of the same size. And consequently, actually, I don't have the problem of finding the first, best, or worst whole, because for me, all of the pages are equivalent. It doesn't matter which page is given to me. So just get the first available page, that's good enough. And you can keep the list of available frames in just a simple, for example, linked list. So just remove the one from the head. We don't care which specific frame that is. When you're splitting the memory into frames, well, everything is, of course, in powers of 2. So it should be a power of 2. Earlier, the frame sizes used to be around 512 bytes. Now it's completely up to your design, but typically the value of the frame changes between half kilobyte and 16 megabytes. On different systems, you will have different frame sizes. But as you can see, all these numbers are powers of 2. A program can now have many pages. And as we said, we don't have that external fragmentation problem here. But still, there is the problem of internal fragmentation. That means the size of a process typically will be, again, multiples of pages, because we're always splitting the address space into pages. The last page, in the last page, you will have internal fragmentation. Because, for example, if your page size is 512 bytes, but for the last page, you're left with 400 bytes. Then you will have 112 bytes remaining left over. So there you will have internal fragmentation. But the amount of internal fragmentation will be small. Again, assuming that there's no bytes, typically there isn't. The internal fragmentation we will have will be on the average half the page size. So if your page size is 512 bytes, it would be 256. But if it's 16 megabytes, then it is 8 megabytes. This also shows us a drawback that we're going to discuss later. How do you now translate the address? Remember, the CPU generates the logical addresses, and you have to translate the logical address into a physical address. To do that, you take the logical address and split it into two, not two equal parts, just a different number of bits for them. Like the first part will be containing the page number. That would be actually an index into the page table, in other words. So whatever the size of your page table is, the number of bits here should be, of course, log base 2 of the size of the page table, because this is, as I said, the index into the page table. And what you have in here is the page offset. That means whatever byte you're trying to find in that page, that will be the offset of that byte starting from the beginning of the page itself. So, for example, if you're talking about 512 bytes, in 512 bytes, you will have bytes from 0 to 511. Okay, so since log base 2 of 512 is 9, because it's half a kilobyte, the number of bits here, the value of d, in other words, the number of bits here for page offset would be 9, because the offset would be between 0 and 2 to the 9 minus 1. And the number of bits here for the page number would be whatever the number of bits for the whole address is. Let's say it's m, that would be m minus n. So for some given logical address space of size 2 to the m, the page size would be 2 to the n, and the number of pages would be 2 to the m minus n. So this is what's really happening. From the CPU, you get a logical address. You split the logical address into page number and the offset. The offset is not to be changed. So separate the offset, keep it in hand for the moment. Take that page number. As I said, the page number is the index into the page table. So find the corresponding element in the page table. The content of that element at index P would be the frame number in the physical memory. So take that and replace the value of P here with the value of F here. And F concatenated with the offset that comes directly from the logical address constitutes your physical address. Note that we don't change the offset, because the offset, remember, is the position of the byte we are searching for in the page. Since the page directly corresponds to the frame, it would be the same byte number also in the frame. That's why we don't translate the offset at all. And this we already discussed. So here we have an example. Just for the sake of the example, we're taking it very simple. Let's assume that A, B, C, D, E, not just letters, but contents, the page contents, okay? Whatever it is, I don't care. So I have the content A, B, C, D in the first page. So here my page size is what? 4. So assuming these are, for the sake of simplicity, let's assume this is byte addressable system. So each one is a byte. So in this example, our page sizes are very, very small for the sake of the example, 4 bytes. So in each page, I have 4 bytes. Okay. I also have 4 pages from page 0 to page 3. So in the page table, therefore, I have 4 entries. Page 0 is placed in frame 5. Page 1 is stored in frame 6. It's going this way. So this part is, so let me just write it 1 second. Let me get the pen. So this is, I'm just writing the frame numbers here. So let me say these are for the frame. This is frame 0, 1, 2, 3, 4, 5, 6, and 7. And these are what you see in here are the byte addresses. So from 0, 1, 2, 3 are in frame 0. 4, 5, 6, 7 are in frame 1. It goes this way. So, sorry. Page 0 is in frame number 5. So it's in here. Page 1 is in 6. Page 2 is in 1. And page 3 is in 2. So when I want to read, let's say, all bytes in this process, from the beginning till the end, for logical address 0, it will be, the address would be like page 0. So let me put it this way. This is the page number, and this is the offset. For 0, it would be 0, 0, 0, 1, 0, 2, 0, 3. Would be for the first page. For the second page, for 4, for example, it would be page 1, 0, the offset 0, sorry. For 5, it would be page 1, index 1. So this is 4, this is 5. Or if you want, I can write it this way. For 6, it would be 1, 2. For 7, it would be 1, 3. It goes this way. Okay, so if you take these addresses in binary and split it, you will find that, because, for example, the address 3 would be what? 0. Sorry. Let me undo that. How can I undo that? Sorry. Sorry. Let me take the eraser. Yep. 1 second. So for the address 3, for example, 3 is what? In binary, 1, 1. We have here in total 16 bytes. So our addresses should be in 4 bits. So this part would be P, this part would be D. So this corresponds to 0, this corresponds to 3. That's what I have as 0 and 3 here. For example, for the case of 6, it would be what? In 4 bits, 6 would be 0, 1, 1, 0. Okay, so this part would be P, this part would be D. So page number is 1, offset is 2. That's what you have in here. That's how I got those. Okay, so this way I can have once again, ABCD taken from frame 5 in that order, A, B, C, D. Then I go to frame 6, where I have the next 4 bytes. Then I go to frame 1, then go to frame 2. So how can we calculate the internal fragmentation? If our page size is given as 2 kilobytes, and if the process size is, let's say, 72,766, then we will need 35 pages, 35 full pages, but we will be left over with 1086 bytes more. That means in total, I will need 36 pages. Okay, 35 of them completely used. The last one is not completely used. Remember, my page size was 248. So in the last page, I have 1086 bytes remaining. So the internal fragmentation would be the difference. So 962 bytes are actually wasted here in this paging scheme because of internal fragmentation. But note, this is just this example. Change the process size, it will be a different value. Or if you change the page size, again, it will be a different value. More or less pages, but the fragmentation would be typically different. The worst case fragmentation you can have is whatever the frame size is minus 1 byte. That means in the last frame, you have only 1 byte. So you have the whole frame or page. Remember, frame size, page size, they are the same. So in the last frame, you have to allocate the whole frame. Remember, you cannot allocate a frame partially. So you allocate the whole frame for that process, but it's using only 1 byte of it, and the rest is wasted. So that would be the worst case internal fragmentation you would suffer. The best case would be 0 bytes. You're lucky because in the last frame, you're using all of the bytes. On the average, it would be half of the frame size. So, for example, if you have a page size of 2 kilobytes, on the average, you will be wasting 1 kilobyte. So, to decrease internal fragmentation, I would prefer smaller pages because the amount of internal fragmentation is directly related to the frame size or the page size. Therefore, if the page size or frame size is smaller, fragmentation, internal fragmentation would be less. However, if the page size is smaller, you will have more pages in the page table. Remember, the page table is an overhead, something you need to keep in memory to manage the memory. Okay, so small frame size is good in terms of internal fragmentation, but it is also bad in terms of page size. That means overhead. So there is a trade-off between the two, and we know that in newer systems, as memory becomes cheaper and more widely available, we can have larger pages because since now memory is cheaper in modern systems, we don't care so much about internal fragmentation. So performance is more important for us. So that's why the page sizes are growing over time. Now, remember that the page table is kept in the memory. That's why I'm saying it's a kind of overhead. So what we're going to do is actually something similar to what we did earlier with the addresses. The page table, also keep in mind that there is one page table for each process. Okay, so that means if you have 100 processes in your system, then you have 100 page tables. At any point in time, if you have a one processor, one core system, take it the simple case, that means at any point in time, only one of them could be in the CPU, then you should be looking at that process's page table. So each page table for each process is in different places. So when a process is in the CPU, which page table am I looking at? To keep track of that, we will have a page table based register, which shows the beginning of the page table, in other words, where the page table is. Different processes will be of different sizes. Therefore, their page tables will be of different sizes. So we will also have a page table length register. Okay, so that gives us the size of the page table. Now, if you add the value of the length register on top of the base register, you will get the ending address of the page table. So any address that's created should fall into a page in that range between the base register value and base plus length register value. Now, one other bad thing about page tables is, now in order to go somewhere in the memory, you have to first go into the page table. Remember, let me go back here. The address that's generated from the CPU is not directly fed into the memory. You first go to the page table, which is also actually somewhere in the memory. That's also somewhere here. Just logically, we're showing it here. So that means you first go somewhere in the memory for the page table. You get the frame number from there. And then using the frame number, you construct the physical address and go to the main memory. Once again, that means you're going to the main memory twice. And remember, we said going to the memory is not very fast. So you need to go to the memory twice. But that's the drawback of paging. Remember, paging helped us to get rid of external fragmentation, which was a very important problem. Later, we will see that with virtual memory, paging will help us even more. So paging is something very good. That's why we prefer paging, and paging is really being used in modern systems. But it also has a drawback that to access somewhere in the memory, you need yet another access. So it introduces really some overhead. It's both consuming memory space and also it's making things slower. So to speed up the access to the page table, we have something called the associative memory, or it's also called the translation look-aside buffer, TLB, same thing. The idea is actually the following. There's some special kind of hardware. Actually, it's some special kind of cache that is able to do searching in all of its entries at the same time. So this is the TLB. This is the associative memory, in other words. In TLB, you have these rows. So each entry here, each row is actually something from the page table. So it's a cache for the page table, but not the full page table, because the page table, as we will see, could be very large. You cannot fit the page table into TLB. But the nice thing about TLB is, if you're trying to find some specific the frame number for a specific page number, you can go you can do a search in the TLB in a very fast manner. This is hardware that is specifically designed for that purpose. If you're looking for a page number, you give the page number to TLB, and TLB will do the comparison in all of its rows simultaneously. All of them will fail, but one, in the best case, if what you're searching for is already in the TLB. That's what we call a TLB hit, because you've hit a row that's already in TLB. If so, you will get the corresponding frame numbers from here. If there is a TLB miss, that means you ask the TLB once. TLB does not, unfortunately, contain the information for that specific page number, since this is only a cache. Then you have a TLB miss, then you need yet another access to the memory. From the memory, in the regular way, you will get the frame numbers from the page table, and either coming from TLB or coming from the real page table, you will get the frame numbers, which will be suffixed with the offset coming from the logical address, and thus you have the physical address. So this is a faster way of accessing the getting the frame numbers. But as I said, it requires some specific hardware, which is called the translation look-aside buffer or the associative memory. Now, what is the effective access time if we make use of the associative memory or TLB? So let's assume that the time it takes to find the frame numbers by giving the page numbers into the TLB, of course, that also takes some time. Let's call that epsilon. So epsilon time units, whatever it is. It could be, for example, less than 10% of the time to access the memory. That's why we're making use of associative memory. It should be fast. And let's say the probability of a hit, the hit ratio, is alpha. Okay. Then the effective access time is the weighted average of the time to find the address by means of TLB if there's a hit. Otherwise, if there's a miss, then also the cost of going to the memory, because remember, if you make a miss, then you have to go to this memory location. Okay, go to the page table. So there is you both look at TLB, so you have that cost of epsilon, but you also have an additional cost of memory access. Well, in both cases, what you're searching for is, finally you have to go to the physical address. So there is always a cost of one memory access to get the real item itself. But if you find it through TLB, then you have a cost of epsilon added on top of that. If there is a TLB miss, then there is a cost of going to the TLB plus going to the memory for page table plus finally again going for the item. And that's what we have in here. With probability alpha, we have a hit. In that case, we have the cost of going to making use of the TLB plus finally, when you construct the physical address, we said you have to go to the physical memory and get the item. So that cost. So that plus one stands for that. But if there is a miss with probability 1 minus alpha, then you have to go to the TLB. You have to go to the memory to get the item. But before that, you have to go to the memory to get the page table entry. So that's why instead of plus 1, that's plus 2. So that would be the average. So for example, if our hit ratio is 80% and the time to access the TLB, to do a search in TLB is 20 nanoseconds, whereas the time to go to the memory is 100 nanoseconds. In that case, the effective access time would be 100 nanoseconds, but typically we want the TLB to have a much higher hit ratio. So if you have a hit ratio around 99%, then the effective access time would be slightly more than 100. So most of the time, because with 99%, you're finding what you're searching for with a cost of 20 nanoseconds. With 1% of the time, you're finding it with a cost of 129 nanoseconds, 100 for page table and 20 for the TLB. Now, this is for fast access into the memory. However, not all of the address space of a process is always in memory. Sometimes part of the page table, in some items in the page table, might not have corresponding frames. This will make more sense later when we start talking about virtual memory in more detail. But just keep in mind that, for example, the last few pages uh, could not correspond to real frames here because you don't have such frames yet. So we would say some items, some entries in the page table do not have valid values. But anyways, you will have a value here. Even 0 corresponds to frame 0. Therefore, we have an additional bit, the valid bit, which is valid if it's 1, if it's 0, it is invalid. So this way you can know if you should actually first check the valid bit. If it's not valid, don't care about the frame number there because it's not a valid frame number. Now, paging allows us, as I said, paging is very popular. It's used in almost all modern operating systems. Paging allows us to share the pages between the processes. For example, you might have processes that are, for example, using the same binary code for the instructions. For example, at the same time in a system, many users, for example, could be running, let's say, the web browser or the GCC compiler or some editor if you're editing files like Emacs, whatever. So for each process, you don't want another copy of the editor in the memory because actually, since the instructions are read-only, remember you don't modify the instructions, so the what's called the text segment, which was the segment that contains the instructions, that part is read-only. So why do I, if let's say 100 students are editing their code in the editors, and they're all using the same editor, Emacs, Eclipse, C-Line, whatever editor, okay? Why do I have 100 copies of it? Because it's the same thing. Of course, in each process, the rest, like the stack, the heap, the data segment, they should be unique for the corresponding process. But the text segment is the same. So such read-only code, which is called reentrant code, is actually the same. So I could share one copy of that. This way I will be saving a lot of space. Also, it is good for inter-process communication, like for shared variables. You can keep them in a shared page. So for many purposes, making use of shared pages is very good. It will help us save time, and also it will even help us in, for example, inter-process communication. That's also true for buffer spaces and others. It's also true for example, when you fork a process. When you fork a process, remember, actually the instructions are the same. So all the shared pages or the same pages will be stored once in the system. So here we have an example. Let's say processes P1, P2, and P3 are running the same editor, and the editor's instructions are consuming 3 pages. Okay, so it is add 1, 2, 3 pages. Okay, you put the editor, you put the editor code in these 3 frames, which are 3, 4, and 6. So in the page tables of P1, P2, and P3, the first 3 pages correspond to the same frame number. In other words, This one, let me just point here, but it is true also for this one, even for this one. So you keep a single copy of those pages. However, for the case of data page, like the data segment, whatever, unique parts, that's different for each one. Like it's 1 here, 7 here, and 2 here. So each one has its own data page, but the others are the same. So how about the structure of the page table? The memory structures for paging can become huge if the process sizes also get larger. For example, let's consider a 32-bit logical address space on a modern computer. The page size, let's assume, is 4 kilobytes. So that means 2 to the 12 bytes. Therefore, that means I need 12 bits for the offset. Then the page table would have what? If I have 32-bit addresses, my address space is 2 to the 32. That's divided into pages of size 2 to the 12. So there are so many entries, and that happens to be 2 to the 20, which is 1 million entries. Actually, slightly more than 1 million, of course. 1 mega entries, let me say. If each entry in the page table takes 4 bytes, okay, then it is 4 megabytes of physical address space over memory for the page table alone. Okay, so I have 1 million entries for the page table. Okay, and if each one is 4 bytes, that means the frame number is, if each frame number is consuming 4 bytes, the page table itself will consume 4 megabytes. That's the overhead you're introducing. This is for the 32-bit system. If you start talking about 64-bit system, then it would be what? It would be 2 to the 64 if we assume the same page size. Pay attention. 2 to the 64 divided by 2 to the 12. So 2 to the 64 minus 12, which would make 2 to the 52 entries. Then multiply it with 4 bytes. See how large it would be. Okay, so the page table itself, in other words, could be quite large. And that will cost us a lot. That's a lot of memory consumed. And we don't want to allocate contiguous space in the main memory, even for the page table. Remember, even for the processes, I don't want to keep contiguous places. Why would I want to have contiguous space for the overhead? Therefore, I would like to actually page the page table. In other words, have a page table of page table. So that's called hierarchical paging. We will also talk about hashed paging. That's quite also effective. And we will finally talk about inverted page tables. We'll talk about these one by one. So let's start with the hierarchical page tables. So these are the 3 possible solutions for huge page tables. So you break up the logical address space into multiple page tables. It's actually a 2-level page table. So in other words, we are paging the page table. So here we go. This is the rightmost one. This is the real physical memory. And this is the page table. Okay? But we keep yet another level of page table. Since the page table itself is a part of memory, why don't I use paging for that one? So I have here two levels of paging. So when I try to access a memory address, I will first go to the outer page table. That page table will tell me a page in memory which contains a part of the page table. If, for example, the address I'm searching for falls into this page in the outer page table, it will tell me where these pages are in the memory. I will go and pick the correct one, let's say the one here, and from there I will be able to find the correct physical frame. So again, assuming that we have a 32-bit machine, and assuming this time the page size is 1 kilobytes. 1 kilobyte, remember, means 2 to the 10. So we divide 2 to the 32 by 2 to the 10, which gives us 2 to the 12. Okay, so I need 12 bits for the page number, because the page table will have 2 to the 22 elements. And inside each page, since my page size is 1 kilobyte, I'm going to have 2 to the 10 bytes there. So I need 10 bits because of this, 10 bits for the offset. So the logical address will now constitute of two entities, P1 and P2, for the page numbers. P1 is for the outer page table, and P2 is for the corresponding inner page table, whichever one is being pointed to here. Okay. So since the page table itself is paged, we have to split that page number, as we said, into two pages. How am I going to do that? Remember, I have 22 bits for this part in total. So here I should have 22 bits, and this part is, we said, is 10 bits. Now, I'm going to split this page table into, again, pages. What's my page size? My page size, remember, was 10 bits. So it has to be, again, 10 bits. So for the second level, it again has to be 10 bits. So whatever remains is for the first part. So in other words, in the outer page table, here I have 2 to the 12 or rows. In each one here is 1 kilobyte, because this is also 1 kilobyte. It has to fit there. Okay. So this is how you have two-level paging. From the logical address, you have P1 and P2. P1 tells the index into the outer page table. P2 tells the index into the other page table. From there, you will get the value of, you also add the value of D on top of that. So this is also called the forward mapped page table. Now, if you have 64-bit logical address space, even two-level paging typically will not be sufficient. For example, if we increase the page size from 1 kilobytes even to 4 kilobytes, so it's 4 times the previous page size, it's 2 to the 12 bytes. Then, as I said, you will have 2 to the 52 entries. So if you have two-level paging, it will be, again, 10 bytes here, 10 bits here for the inner page. But we will have the outer pages of 42 bits, okay, which is quite a lot. So Instead, for example, I can have this time 3-level paging. Okay, so P1, P2, and P3. 10 bits here, 10 bits here, and the remaining here. So this way, you can increase the number of levels in paging. How about hashed page tables? Now, hashed page tables are typically common in address spaces that are more than 32 bits, so typically for 64 bits. The virtual page number is this time hashed into a page table, and this page table contains, since we're talking about hashing, it's a hash bucket. So there you have a list of the corresponding items. So each element contains the virtual page number and the value of the mapped page frame and a pointer to the next element, just like in regular hashing. So you take the logical address. The first part is the page number that you apply through a hash function to the hash table. So it falls in here. And from here, you look at the list to find P. The first item here is Q, so not that one. Look at next. That one happens to be P. Okay, that's fine. If not, you keep on searching for it. If you cannot find P at all, then that's an illegal address. Whatever you find, when you find the item there, the second element here will be the corresponding frame number. So take that frame number and append it with the offset, and that will be the physical address. However, when you look at this, you see that there could be many, many pages. And remember, there are also many, many processes. So it's many processes times many pages in all. So the number of possible pages would be huge, extremely huge. However, the number of real physical frames in the memory is limited. That's what we know. That's obvious. So one solution at this point is using the inverted page table. So rather than each process having a page table, and then you try to keep track of all possible logical pages and hopping, as you can see, for example, in the case of 3-level paging, you go once, twice, 3 times. So you hop, hop, hop to get to the final address. Instead, you look at a table which is stored in just the reverse order. Remember, we try to associate individual pages with the frames. It's an inverted page table. So it's just the inverse. It says this frame belongs to this process, this page. Okay. So once again, remember, every process has its own page table. So to find a specific page for a specific process, you go to that process's page table. You go to the in the page table, you find the element for that page table. That element contains the frame number for that specific page. In other words, you're translating, you're storing the information where each page is stored in a frame. So the page number is converted to the frame number. In the case of inverted page table, in that inverted page table, what you're storing is this frame belongs to this page. This frame belongs to the other page. This belongs to the other page. But remember, in the physical memory, you have pages of different processes. So it's not sufficient to give the page number, but you should also search for, you should also make sure that it's the correct process. Therefore, not only the page number, but we're also keeping the process ID. So in the inverted page table, this time, we're not storing here the frame number, but what we're storing is the tuple, process ID, and page number. So if you're trying to find this logical address, PD is your logical address, but that logical address belongs to process with PID value, with process ID PID, then in the inverted page table, you'd search for the tuple PID and page number, PID and P. Now, it's different processes and different pages here in all inverted page table. But there is one entry in the inverted page table. There is one entry for each frame. In other words, the size of the inverted page table is limited. There's only one page table in the system, and also the size is limited. The size is equal to the number of frames. There is one entry per frame, in other words. And you find the entry that contains the PID and P tuple you're searching for. Whatever the index for that entry is, that's the frame number you're searching for. So take that index and put it as the frame number, followed by the offset. That will be your physical address. Now you have to do a search here. So that search will take time. So translation look-aside buffer is a good solution also in here. So this inverted page table, remember there's only one and it's of limited size. So you can, if you have a sufficiently large translation look-aside buffer, you can store the whole inverted page table in TLB. And when you're searching for a specific PID and page number, it will immediately find it for you.